Welcome back to this course on advanced memory hierarchy design. In this lesson I will describe two compiler techniques, merging arrays and loop interchange, to reduce the cache miss rate. I will now discuss data reordering techniques that a compiler or you, the programmer, can apply. The first technique is called merging arrays, and it is based on the observation that some programs access multiple arrays with the same index at the same time. Furthermore, these accesses can interfere with each other, which may lead to many conflict misses. Here's an example, computing the dot product of two vectors a and b. Suppose now that we have a direct map cache, that the size of a and b is a multiple of the cache size, and that a and b are consecutively allocated. This is not uncommon since the cache size is always a power of 2, and arrays whose size is a power of 2 are also very common. Then every access to AI and BI will result in a cache miss. So spatial locality is not exploited at all. You don't believe me? Well, let me explain it on the next slide. Here are again the assumptions that I made and the code example that I am using. To make this example a little bit more concrete, let's assume also that there are two double words in a cache block. So A and B are allocated in memory like this. First comes A with 2 elements per block, and then comes B also with 2 elements per block. Consider now what happens on the first iteration when A0 is loaded. The block containing A0 and A1 is loaded into the cache. We need to multiply A0 with B0, so now we load B0. Under these assumptions, A0 and B0 map to the same cache block, so the block containing B0 and B1 will replace the block containing A0 and A1. On the next iteration, we need to load A1. Oops! It was in cache, but it was replaced, so we need to bring it in cache again. The same will happen when we load B1, A2, B2, etc. Every access will replace data that is needed in the following iteration, and therefore every access to the data cache will miss. The merging arrays technique merges or interleaves A and B so that AI and BI will be in the same block. Here's our code example again, computing the dot product of two vectors a and b. Here's the code after array merging has been applied. Instead of using two arrays a and b, we use one array of structures with fields a and b and modify the code such that one iteration multiplies the fields of a single structure. This technique reduces or eliminates conflicts between corresponding array elements and also improves spatial locality, since when we load the field A, we also fetch the field B, since it is contained in the same cache block as A. How many cache hits will there be when we apply array merging? Let's look at the previous example again. Here at the top is the code after array merging has been applied, and the figure on the left shows the memory allocation, assuming again that a cache block consists of two double words, and in this figure on the right I will show the content of the cache after every access. First, our code accesses field A of x0. If it has not been accessed before, it will be a compulsory miss and the entire x0 structure will be brought to the cache. Then field B of x0 will be accessed. It has been brought to the cache by the previous miss, so this access will hit the cache. Then field A of x1 will be accessed. We again incur a compulsory miss and the entire x1 structure will be loaded into the cache. Then field B of x1 will be accessed. Again, thanks to spatial locality, this access will hit in the cache. So overall, instead of 2 n misses that the unmerged code will incur, there will be n misses. In other words, we have reduced the number of misses by half. The previous example makes a nice exercise. What would be the hit rate of the data cache if the block size would be 32 bytes, 4 doubles, instead of 16 bytes, 2 doubles? Many scientific papers and code optimization handbooks mention array merging. To add a bit of confusion, however, they use a different name for it. Merged arrays are also known as the array of structures data layout. Unmerged arrays are also known as structure of arrays, even though they are not commonly encapsulated in a structure. It is also possible to mix the array of structures and the structure of arrays data layouts. This leads to data layouts such as array of structures of arrays, AOSOA, also called tiled AOS, or SOAOS. To give an example, here's an example of the structure of arrays layout. Two arrays are merged in a single structure. And here is the corresponding array of structures data layout that we have seen before. Corresponding elements of the arrays A and B are merged into a single structure. And here's the array of structures of arrays data layout. Now a structure consists of two small arrays that are 4-element subarrays of the original arrays A and B. Depending on the access pattern and the cache block size, this layout may actually perform better than array of structures. The next data reordering technique, or actually data access reordering technique, since we do not reorder the data but the order in which they are accessed, is loop interchange. It is based on the observation that some programs have nested loops that access data in a non-sequential order but in a strided fashion. This may lead to poor exploitation of spatial locality. When loop interchange is applied, the nested loops are interchanged or swapped so that memory is accessed in sequential order. Accessing consecutive memory location reduces the number of misses by improving spatial locality. It must of course be legal to interchange the nested loops. It's not always legal. Here's a code example. We have two nested loops. The outer loop uses the index j and the inner loop uses the index I. In iteration ji, element ij of the matrix X is accessed. So, for example, the first element X is x00 and the second element accessed is x10. But in C, the elements within a column of the matrix are not stored consecutively. So x00, for example, is not contained in the same block as x10. This shows the code after applying loop interchange. Now the loop with index I is the outer loop and the loop with index j is the inner loop. Now the first two elements accessed are x00 and x01, which, at least in C, will be consecutively stored in memory. Whether loop interchange is effective depends on how two and higher dimensional matrices are stored in memory. C stores matrices in row major order. This means that consecutive elements within a row are stored consecutively in memory. Fortran, on the other hand, uses column major order. Here's an example, a matrix with 2 rows and 3 columns. If row major is employed, the matrix is flattened like this. First, the first row is stored, element 0, 0 to 0, 2, and then the second row, elements 1, 0 to elements 1, 2. On the other hand, if column major is employed, the matrix elements will be stored in memory like this. First, the first column is stored, A00 and A10, then the second column, and so on. Let me now illustrate how loop interchange reorders the data accesses. On the left of this slide, I show the code before and after applying loop interchange, and on the right, I will illustrate the order of data accesses before and after loop interchange. Before loop interchange, the first element that is accessed is this one. This is the second one that is accessed, and this is the third element that is accessed, and so on. When all elements in the first column of A have been accessed, the code will access the first element of the second column, which is A01. However, if the matrix X is too large to keep in cache, it probably is, the cache block containing this element A01 will have been replaced. So spatial locality is not exploited at all. After applying loop interchange, this will be the first element that is accessed. This is the second element that is accessed, and this is the third element that is accessed. So now we access the elements in the order in which they are stored in memory, which improves spatial locality. Bottom line, in this example, loop interchange makes sure that we get sequential access instead of jumping or striding through memory every 100 words, which improves spatial locality. This concludes this lesson. Thank you for watching. In the next lesson, I will describe another compiler technique called blocking or tiling that aims at reducing the miss rate. Stay tuned.